Okay, good afternoon, everyone. I'm Shenqi. Today I'm going to present a paper, Self-Distillation written on policy self-distillation for large language models. This work studies a very interesting question in LLM post-training. Can a model improve its learning ability by learning from its own policy rollout, while it can still receive dense supervision similar to distillation? So the key idea of this paper is that a single model can play two roles at the same time. A student which generates responses in the normal way, while a teacher which will be given a privileged information. So this will create a training framework that they call the Unpolarized Self-Distillation, or OPSD, where it's very popular nowadays. Okay, now see the background of the LLM post-training. As shown in these three lines, there are two major directions. The first one is the supervised fine-tuning, or more generally, the off-policy distillation. In this setting, the model learns from a fixed dataset or teacher-generated dataset. The advantage is that the supervision is dense at the tail level, so optimization is usually stable and efficient, but the limitation is that the training distribution is fixed in advance. So the model is not learning from its current behavior. Another direction is about reinforcement learning, or the RLHF. So these methods are on policy because the model samples from its current policy and learns from those trajectories. It gives better alignment with actual model behavior, but the training signal is often sparse and will have high variance. This paper now positions policy distillation as a way to combine the strengths of both the policy sampling and the dense token level rewards. Okay, let's see something about policy learning. Here is an example. What on-policy learning means, the main intuition is simple. On-policy methods learn from what the current policy is actually doing. This is a classical example, SASA. The state action rewards state action, where the update depends on the action that the policy really takes in the next state. So the message here is that the data distribution is coupled with the current policy is important because it reduces the mismatch between training and inference. In language models, that mismatch is often called exposure bias. If we only train on these fixed trajectories, the model may struggle when its own generation drifts away from those trajectories at that time. Another example is about the trace playing. So on policy reinforcement learning, will like playing four games entirely on ourselves own without a coach. The final feedback, no matter we win or lose, it will come directly from our own decisions. So it's highly relevant to how we actually play. But the problem is that the feedback only arrives at the end of the game, so it's not clearly tell about the specific moves. On the other hand, the off-policy distillation is different. It's like more like watching a grandmaster play. So we can get access to very high quality moves and very strong strategies. However, these moves there will be demonstrated in board populations. Maybe it's difficult for a beginner to understand what's actually if it's naturally to reach this position. So although the signal is rich, it's not always aligned with the situation comes from the student's own play. So what we really want you to combine the strengths of both. We can also see the math questions here. We have two examples. One is the off-policy distillation, the other is on-policy. The difference is that whether we train from the teacher trajectory or the student trajectory. So for the off-policy distillation, we train on teacher trajectories. The complete sequence of generated tokens, including intermediate thinking steps, we can use the such full next token distribution at each step. The student updates towards each token, and this is in the sequence, and the proportion will try to show how likely it was to generate the token itself. And we can see the most unlikely one is in dark red. The drawbacks of such a pattern is that the student learns in context frequently by the teachers, not the ones the student itself often then find itself. So it may cause some compounding error, or maybe if the student makes an early mistake that the teacher never teach, it will find itself diverging much farther from the state it's observed in training. So we can see another example on policy distillation is the below one. The core idea of it is to sample trajectory from the student model and use a high-performing teacher to grade each token of each trajectory. So returning to the such an example, the policy distillation would score each step, and it will try to make each step of the set solution, punishing the mistakes that cause the student to arrive at the wrong answer. So this is some background. Now let's formulate the problems on policy distillation. The basic concept is that the student policy first generates output from its current distribution. Then, instead of only receiving a scanner reward, is trained using a richer teacher signal, which you can see is the pi star. So compared with standard supervised learning, this framework is more adaptive because it follows the student's own rollout distribution. You can see all the sample, they are from the pi theta, the student's trajectory policy. So this is a conceptual bridge that motivates the OPSD. The authors want to ask if we can use the student itself to serve as a teacher. So in this paper, they claim some benefits of the policy self-distillation OPSD. First, such a single model can teach itself. There is no external larger teacher, so it's more efficient. And second is on policy. So the learning signal is computed on the student's own route, which means the training distribution stays aligned with the model's current behaviors. The third is that it can provide dense feedback. Instead of only use a sparse scalar reward like GRPO, OPSD uses a token level distribution matching, which gives a much richer learning signal. And finally, the paper claims that the major efficiency gain, around 4 to 8 times better token efficiency than GRPO. It's very huge. So this is an example of the motivation. If the student have the key statement is that the evaluation is easier than generation. So we can give the student a reference book to make it self-rationalization. In this way, so the OPSD leverage such a asymmetry. The students can still operate in the standard way while it gets the privileged information, or we can say privileged context to teach itself. So this is why it's called the self-distillation. Let's make some comparison with existing framework or methods. This table we can see it compares different training paradigms. So this depends on whether they use policy data or dense learning signal or the sampling cost or external teacher. We can see that a proposed OPSD can combine all these benefits. They are policy and they have dense signal. Of course, they have low sampling cost and they don't have external teacher. Let's see the overview of the framework of this paper proposed OPSD. So basically, from left to right, we have the data set. We have such a pair, the X and the Y star. X is the question, the problem solution, and the Y star will be given as the COT because since the COT plus answer is given in the data set, this is the learning task. And after that, we can see in the middle subfigure, we have the student prompt, teacher prompt. So we have two prompts here. One is in red, the other is in green. So we can get the student policy and the teacher policy. From student policy, we can do the policy sample. We can just say sample from the student. And from that, we will get the white hat. After, since after we get the white hat, then this will try the teacher prompts now. It includes the question, the white star, the privileged information, and the previous context. So which will allow it to produce a more informed token distribution. The last one is the learning objective. This adopts a per token divergence. So basically, the student sample after the student sample the rollouts, each clicks of that overall rollouts, we ask the student predict what the teacher predicts under the conditioning, and the loss will be calculated within such a formula. We can see the process in another way. So we have the student policy and the teacher policy. Teacher policy will be given one more privileged information, the white star, so it can have a better teaching ability. And the sample will be done by the student itself to make it more efficient. And we can, after that, you can see in the below, we will get the policy of the student and the teacher. As we just mentioned, what's one important conception here is the privileged information white star. So maybe it's like some prompt engineering. We can see that the student prompt here is straightforward. It only contains the math problem and asks for the answer. And in the meantime, the teacher prompt, we also have a prompt and the answer. However, we will try to include a reference solution or COT in the middle of the problem and answer. So if we use such a screen language solution as context, it will produce a more informative next token distribution. In other words, the teacher acts like a rationalizer or expander of the correct solution. So it's a very important point. The OPSD is not only trained on touch tokens directly, it's training on the students to align its distribution with a more informed teacher distribution under the same rollout prefix. So let's see the last part about the training objective. In this paper, they introduced two kinds of training objective. One is the full vocabulary divergence. The other is based on the sample token distillation through the policy gradient. We can see one by one here for each position the student generated response. We will compare the next token distribution of the teacher and the students. And the students not only learns the sample token, it learns the teacher's full preference over the whole vocabulary at each step. So this captures much richer information. And about the sample token, we can see the difference is that's not the whole distribution. It's the yn hat now. So such a method, such a trick can be found in last year's Thinking Machine Lab's blog, the on policy distillation. They have adopted this method in their platform, their training API. Anyway, it's where in this formulation we can only look at the sample token now, and we need to use the policy gradient because the sample operation they are discrete. It's not we cannot derive on that. That's why we need the policy gradient. In the later experiment, we will see the difference, which will be better in the reasoning task. Another theory about the JS divergence. As below, we have the forward divergence and the reverse divergence. And in this paper, they try to get a balance. So they have adopt the general Jensen channel divergence, and the beta parameter they adopt is 0.5, so it's very balanced. What's the difference of the forward KL and the reversed KL? Basically, the idea is that if the teacher distribution has multi-models, then minimizing the forward KL often encourages the students to spread the probability mass broad in order to cover them all. So we can say it's mean seeking. On the other hand, the consequence of the reverse KL is mode seeking. In this situation, the students may concentrate on one high probability region and ignore the rest of the teacher distribution. This can lead to some model collapse, where the student keeps repeating a narrow style of answer that seems safe. Yeah, so maybe although the reverse scale can suffer from the instability, but it can push itself to seek some specific mode. Yes, that's why nowadays more policy distillation will adopt the reverse KL method. Let's summarize the objective function. So this loss takes an expectation over student rollout, which is on policy, of course. And for each sample, the response from the student, it computes the JS divergence, and this paper defaults to use the full vocabulary. Mm, yeah, this is about the objective function. We can see the algorithm. What's important, I think, is that they have given the privileged information as the first step. So they don't need to generate it during training. And after that, for each mini batch and for each example in that mini batch, the student samples on policy response, and the algorithm will compute the token-wise divergence between the teacher and the student. Yes, so algorithmically, OPSD is very straightforward. We can summarize the training cycle. So first is about the student sampling, and this will generate a trajectory-wise star, only one throughout on policy, and evaluate it with the teacher with the white star, the privilege information, and only update the logic in student model. Finally, we can see the experimental setup. This paper focuses on the learning task. They use the QN3 instruct family. And the training data, they use open source. They are problem solution pairs, also with the reference with the COT. The baselines, they use SFT, GRPO, and the benchmark, they use these AIME series and the HMMT, AMO. They are basically they are difficult math tasks. You can see this table. It shows the main performance. From bottom to top, the performance of OPASD gets better and better. For example, 1.7b, the OPSD is 551.4. It's not greater than the GRPO. However, when the model gets larger, its performance can surpass the GRPO. So yes, this is one important scaling law the authors try to claim. The quality of the self-distillation may be limited by the model's overridden ability. I think this is the reason. Another experiment is about the token efficiency. You can see these two plots. They compare the OPSD and the GRPO in terms of the average accuracy across 4 mass tasks. What we can see is that OPSD reaches the competitive or better accuracy much earlier, especially when we talk about the number of the tokens generated. Another performance we can see is the average pass SK accuracy. So similarly, we can conclude that when the model gets larger, when the generated length is longer, the OPSD we can see in the light green, this has the highest result, highest accuracy. So the generation length will be helpful for the accuracy in OPSD model. Which remember we talked about the sampled token and the full vocabulary strategies. So in OPSD, especially for the reasoning task, the author had done some experiments and they proved that the full vocabulary for the logic distillation will have a better result. Probably they have much more consistent and full signal rewards. Let's summarize the contribution of this paper. So this paper, the authors propose a novel framework, OPSD. This enables a single model to act as both teacher and students. And they leverage ground truth answers to provide dense token level supervision on the students' routes. The second point is that they evaluate OPSD on these four competition level mathematical reasoning tasks, and it proves that the OPSD can generate less tokens and achieves a better performance compared with the SOTA method. Some discussion maybe because the first one is that the current framework does not explicitly leverage the correctness of the generated answers. So maybe the generated answers is not correct and the signals may be beneficial for the training. And another point is that the problem difficulty plays a crucial role in the self-distillation. We must guarantee the reasoning ability of the student model. Also, we can try to expand such framework to other tasks like tool use or multimodal reasoning. Finally, we can get some takeaways. So nowadays, we want to towards the self-teaching models. This paper, they leverage the pre-leverage context-wise style to let the single model teach itself. And they also use a dense signal, the full vocabulary, to provide richer feedback than the sparse reinforcement learning rewards. And this method also achieves high efficiency compared with SOTA methods. This is the end of my presentation. Thank you for listening, and I'm happy to take any questions.